Good evening, everyone. I'm Venkat. I'm a PhD student at IIT Hyderabad. I work in the area of intersection of machine learning and compiler optimizations. Today, we are going to talk about a recent work which we call it as ML-LLVM-Tools, which is essentially to seamlessly integrate machine learning models with LLVM compiler. Right, let's start. So firstly, LLVM compiler or any compiler optimizations in general have a lot of heuristic-based hard compiler optimizations. And these can be better exploited by using ML models and to improve their performance. Right, so success of ML has found its place in NLP, image processing, etc., and it has transcended to compilers as well. And it is ML-based compiler optimizations is not a new concept at all, and it has been there from late 90s and to date, right? So ML-based optimizations, when we talk about it, there are a lot of several such optimizations like loop vectorization, loop distribution, function inlining, phase ordering, register allocation, etc., etc. So within LLVM, also we have, in the production branch itself, we have got ML models integrated or aiding in making inlining decisions right from 11.x and recently in register allocation as well to perform better eviction. Right, the scheme of ML in compiler optimizations goes as follows. First, there are a bunch of input programs, and then comes a compiler and set of ML models. Right, the first compiler bundles up the input program and sends it as an optimization query to the ML model, and this query would contain the representation of program in a form of embeddings, or it could also be in the form of features, and it queries the ML models. The ML models goes on to process this input in either training time or in the inference time, and it generates the necessary, makes necessary predictions that is sends back to the compiler. And then compiler goes on to materialize these predictions made by the ML models, and this cycle could go on depending on the optimization setup that we have, right? Upon completion of this optimization cycle, the code is generated and it goes on, right? There could be several such stack of ML-based optimizations which could query different ML models, and it could continue. Right, so this talk is essentially going to focus on the communication aspect, the way compiler queries the model and way the model gives back the response to the compiler. Communication is an important aspect because it determines the usability of the approach itself, right? So it determines the scalability of the underlying ML-based compiler optimization in terms of compile time, in terms of memory issues, so on and so forth. Similarly, it determines the practicality of the proposed approach. So it should be viable to deploy. For deployment, it should be usable, etc., etc. So currently, there is no single standard approach for any communication. Especially, people have been using Python wrappers for the models written in Python, or the predictions are communicated back to the compiler by using compiler flags, or on the other hand, people have been using C++-based APIs for querying models. So there are several limitations when we have such form of communications. Firstly, there are scalability issues. So in our experience, whenever we have used Python wrappers for communication, we have observed something about 6 to 100 times slowdown in comparison to a normal compilation. It is true especially in phase ordering, loop distribution, register allocation, etc. And secondly, it comes to integratability. Not all models, not all outputs can be passed as an input to the compiler by using compiler flags. So especially it is true in register allocation, instruction scheduling, or any complex setups, right? And thirdly, we have models written in C++. These are not very ML developers friendly, right? So people prefer writing models in Python, especially the cases where there is not much support for C++ APIs like RLlib, SciPy kind of libraries. And then we have finally portability. So here, there is really a need for support for diverse ML frameworks. That means A compiler like LLVM should not be particularly tied to a single ML framework, so it should be compatible with different diverse ML frameworks like TensorFlow, PyTorch, JAX, etc., etc. So there is really a need for a scalable, versatile, and a common framework to facilitate ML-based compiler optimizations within LLVM. Right. So in this talk, we propose a framework and architecture-independent infrastructure in LLVM to facilitate both training and inference. If for training, what we propose is a ML-based development would go on in Python within a generic framework, independent of the underlying framework, by using LLVM, by using a gRPC library, which we call as LLVM-gRPC. And for inference, the inference would happen within LLVM, and the trained models would be exported and linked to compiler toolchain during the build time of the compilation of LLVM, right? So this is facilitated by using an ONNX-based library, and we call it as LLVM-InferenceEngine. Okay, so first let us start with the gRPC framework for supporting training. So firstly, there is very clearly a need for a communication between LLVM and the ML models written in Python. This is essentially an inter-process communication. So we use gRPC, which is an open source high-performance RPC, to facilitate this communication. So we integrate gRPC with LLVM, and we build a library called LLVM-gRPC. And the end user who develops the ML models would just implement or override certain API calls in order to enable training, right? So we use this framework in our recent work, which essentially does register allocation by using reinforcement learning. We will talk about it towards the end of this section. Right, firstly, what happens? So user is expected to write a set of protofiles. Protofiles are nothing but protobuf files to serialize the data. So this protofile would contain the message format that would be transmitted between compiler and the model, along with the RPC definition, right? And we have also exposed certain utility functions in the library as a part of LLVM-gRPC. So during compilation or during the build time of LLVM, the proto files are compiled by using proto-C compiler to generate the necessary C files or C++ source files and header files along with the Python files. These files are used later on by the underlying pass and the model to facilitate the communication. So we'll see how the communication happens. Firstly, this is the protofile that we have been talking about. So user is expected to write or define the structure of messages that would be involved in the communication, along with the definition of RPC call. Once this definition is made, upon compilation, this would generate a bunch of C++ and header files. And in LLVM side, what will happen is it is essentially a client-server communication now. So LLVM becomes a server during training time, and Python becomes client. So within LLVM, people have to include this generated header files and inherit the gRPC utility class along with the generated C++ class, right? So and they have to override the gRPC function that was defined in protofile. And along with LLVM-gRPC library exposes some utility functions like to start the service and to stop a service. This run service method is essentially a blocking call that would wait for client to query your RPC call that you have defined. Right? In the Python side, the flow is very similar. Here, people have to use the generated Python code upon compiling the protofile. So here, people need to inherit the generated files and start server and establish a connection. Establish a connection and query the server by making call to the RPC call. So the process as simple as that. We have used it in our recent work on register allocation. So this is based on MIR. The input representation to this is based on MIR-tvec, which is an extension of IR-tvec. IR-tvec is a way of representing programs as vectors to facilitate ML-based training. Right, so what happens is this. So here in C++ side, the mod pass generates the interference graph, and goes on to generate the input representation to the model. And in model side, we have a bunch of agents interacting with each other to generate an optimal register allocation scheme. Right, so once the inheritance graph is generated, it is to be transmitted via LLVM-gRPC framework to the model, and model then acts upon it to generate the predictions. These predictions are transmitted again via LLVM-gRPC to the server, in this case, the LLVM environment, which goes on to materialize the prediction, just like what we have seen in the beginning. Right, and this process in this case is iterative, so the generated say in this case, the agent determines a node to be split. So upon splitting a node, the observation is updated, and the agent goes on to operate on the updated observation. And this process goes on till the end. We have a proper register allocation scheme. Right, so coming to pros and cons of this approach. Firstly, it very clearly provides an ease of development. So it is transparent to underlying DL or RL algorithms, policies, anything. And secondly, it also provides ease of training. It supports multiple GPUs, and also it could support parallel workers for different sample collection in case of RL. And thirdly, there is a reusability of code. So you write the specifications once in protofile, and you reuse in both C++ and Python front. But however, this is insufficient for inference because there is an overhead involved in compilation time, mainly due to the inter-process communication that arises out of this. And also, this is not transparent to the user. So think of a situation where the end user who is using this optimization has to start server and client, and it is not favorable at all. So there is very clearly a need for a better infrastructure to facilitate inference. So that is where LLVM-InferenceEngine helps. So it is a ONNX-based framework. So basically, inference has to be framework neutral, interoperable infrastructure that takes in a trained model and integrates it in an interoperable manner. For this, we use ONNX. ONNX is basically an open neural network exchange. It is a Linux Foundation project, or it can support almost all native languages along with major ML-DL frameworks. Again, we will talk about the couple of use cases that we have based on this inference engine towards the end. So it's a two-step process. First, we have a trained model. The trained model is to be exported from native to ONNX format. Upon exporting, this has to be imported and linked during the compilation build time of LLVM using the runtime, C++ runtime of ONNX. Right. So now, this is a proposed inference flow. Assuming there are a bunch of passes that are making use of RL and ML optimizations. So we have inference engine coming here. So inference engine abstracts out all the unnecessary details, and it is just a single API that you would query and get the final results. So in case of RL, we have wrappers to support multiple agents. The learned model will be imported, and agents will directly interact with them, and environment wrapper classes by using environment wrapper classes, etc. And in case of a normal DL-based approach, it is quite straightforward. You need to just import the model and just directly query the model. Right? And all of these would sit inside LLVM toolchain. And again, the trained model would be exported as ONNX, and it is linked, right, directly. Right, so this is what the end user would be doing. So just inherit, this example shows this corresponds to an RL-based model example. So here we need to inherit the environment class provided by the inference engine. And in case of RL, what we have is that the pass directly giving observations to the underlying model, and the model makes predictions, and the observations get updated by the pass. Right? So we have to inherit the environment here, and then in the actual logic, once the inference engine object is created, we need to just query the underlying model by using a single API call, as straightforward as that. This is true in case of even cases where there are multiple agents that need to be called. So in that case, all we have to do is to just define the schedule of the agents in the order in which it has to be called. And finally, yeah, this is what we achieve by using Inference Engine. In case of RL for real, if you see here, we have blue bars corresponding to the compilation time taken by the greedy register allocator, and the green bars correspond to the compilation time taken by LLVM-gRPC. This is actually the proposed approach which appeared in the paper. And orange bars correspond to the LLVM inference, the compilation time taken upon using LLVM inference engine. Right? As you can see, there is a major significant difference between these two. Still, even though there is a major gap between the regular non-ML compilation flow and that uses compilation flow, even though there is a significant difference, but this difference has also been significantly reduced upon using the LLVM inference engine. So this is true even in case of the POSET RL flow, which is basically a phase ordering application by using reinforcement learning. So even here, we observe about 10 times improvement in compilation time upon using LLVM inference engine. And in case of RL for real, we observe about 12 times improvement. Yes, so why these improvements come in? Because mainly this facilitates in-process communication. There is no RPC calls involved, there is no IO, nothing. And also it leads to a lesser compilation time overhead because, again, due to fact that there is no communication involved. And third is it can provide a framework and model agnostic infrastructure. So users can write models in PyTorch, TensorFlow, anything, and even a single pass can use multiple models within multiple frameworks, and it can go ahead and query. And finally, most importantly, it is completely transparent to the end user who would be using the optimizations. The end user need not know what is going on behind the optimization, which model is being used, and so on and so forth. And finally, we have some related works in this area. Firstly, it is ML-Go, which is part of LLVM. From LLVM-11, it uses TensorFlow APIs, TensorFlow C++ APIs, and recently it has also integrated some raw form of inter-process communication. And yeah, we would like to explore this further to see the support for different RL, ML setups, even for, say, optimizations involving single or multiple communications. And secondly, there is a compiler GIM, which is a GIM framework that provides RL environments for training RL-based compiler optimizations. And yes, in summary, what we have done is we have proposed an infrastructure to facilitate communication or facilitate ML-based compiler optimization in LLVM in both training time and in the inference time. And the training is based on LLVM-gRPC, which is a gRPC-based framework, which operates in a Python, which facilitates the training to happen within Python in a model or framework-independent manner. And when it comes to inference, we proposed ONNX-based library, which facilitates in-memory communication within LLVM, which is also done in a transparent manner to the user. And this framework or this infrastructure is lightweight and it shows more promising trends. And yes, it is a work in progress. We want to explore a lot more and see that even this compilation, even this time is reduced going forward. Yes, you can find more details in the web page that is given here, and thank you.
Any question from the audience?
Yeah, can you show the graph again?
Yes.
So the compile time, so the green one is slower, right? This is.
Yes.
So it takes more time?
Yes.
And you don't have any charts for how much better it actually performed in terms of like how much better the register application was?
See, these blue bars represent the original flow without any ML model being used. And whereas these green bars show the performance upon using LLVM-gRPC. And the orange bars show the times taken upon using LLVM inference engine. So the clear observation is that whenever there is an ML model being involved, it leads to an increase in compilation time. Yes.
Thank you. But do you have metrics of how much that model actually improve the output of the?
How much? Sorry.
Like, was it useful to use the reinforcement learning based
Yes. So we see improvements in register allocation upon using reinforcement learning. Yeah, you can perhaps get more results from the paper itself. I think that is not the scope of this talk. Yeah, that's why we skipped it.
Yeah, so you mentioned like the ML-Go tooling. So like a lot of the stuff like training time and the inference stuff, like there's upstream LLVM infrastructure to interface with TF Lite. And like that should have fairly good portability if you want to go through some hoops. So what's the main advantage of using like your ONNX runtime and your gRPC runtime over what's being shipped upstream with the ML-Go work currently?
Right. So ML-Go, if I'm not wrong, uses inter-process communication to facilitate communication.
Yeah, so the way it works usually is we emit a TF Lite model, and then we're importing that into the compiler like as a collection phase, and then we run a bunch of compilations on that, and then we pull that back and then do another round of reinforcement training. So there's no inter-process communication during the ML-Go training processes.
I see. So recently I came across pipe-based communication which is involved in ML-Go.
Yeah, that was mostly for the compiler gem support as far as I'm aware.
Yeah, so that is one point. And secondly, we try to, this would facilitate that you can use any framework. So you can use PyTorch-based models or anything, yes.
Okay, so mainly model compatibility.
Yeah, correct, that's right.
Thank you.
Hello. Sorry, I didn't quite understand the gRPC flow. I think you mentioned that the LLVM side initiates the server and then Python side is client to it. I wonder why that choice is. I mean, gRPC is bidirectional, so it doesn't. The choice of who is the server depends mostly on what gives you the best performance. Was there a particular reason why you chose LLVM to be the server in this case?
Yes. Mainly it is being used in the training time. So we wanted the Python models to drive the training. So it naturally fits in there.
So they initiate the engagement because they need the data, so they ask for it. Okay, I see. Yeah.
Thank you so much, Venkata, for the great talk. And the session have concluded for the day. Please attend the reception located at the hotel's restaurant, Cass and the Clyde on the lobby level. Thank you very much.